So we are doing numeric differentiation. And from the class I had way back when, I'll give you some of my notes that says there's a profound difference between differentiation and integration of functions. Analytically, for a function specified by a formula, its derivative almost always can be found, but the same function may be very difficult, if not impossible, to integrate. Numerically, the situation is reversed. The accuracy of numerical differentiation is sensitive to the algorithm used and to the numerical noise in the computer. That's why we did that entire section on error. On the other hand, almost any function that does not oscillate wildly can be integrated numerically, and doesn't matter for the method. What I have here is Maple, and I'm going to show you a few cases in Maple. Notice in the typewritten part of the lecture, I did specify sine, and so sine is the function I'm going to use. In Maple, you have to start and you have to declare what packages it's going to use. It only loads what you tell it to use. That's extremely handy because it only uses enough memory to load and do what you want it to do. It doesn't load anything extraneous. It's sort of like C and Java, from what I understand, in that perspective. So here I just wanted to load the calculus package. Right, that's that first line. We are going to use the secant method, or the forward finding method that you had from before, that the book mentions, that forward finding method. And we are also going to use the central finding method, where we take a central point, or the point that we're trying to evaluate is the central point. All right, that's actually called Newton's quotient. That's the f of x plus delta x minus f of x over delta x. In this case, it's f of x plus h. H will be our delta x. And then we will do this. Now, if you're trying to follow along and you want to do some of these computations on your calculator, make certain your calculator is in radian mode. All computer programs run in radian mode, not degrees. So when I say I want sine of x at 0.5, that's 0.5 radians. Now we know that the actual value of sine x, or the actual derivative, of sine x is cosine x. So if you take cosine of x at 0.5 radians, I'm actually doing it while I'm talking to you. That's going to be 0.877582561 on my TI 83 Plus that I have in front of me. Right, so that's the number we're going to be comparing this to, the 0.8775. The first thing that we do, of course, is we're going to take Newton's quotient, sine of x at 0.5. This is the forward finding mode. All right, so it's going to take 0.5. It's going to add 1 to it. So it's going to take sine of 1.5 minus the sine of 0.5 and divide by 1. Notice that's terrible. Right? And you can tell how terrible it is simply by taking a look at the output. Not only do you ask for Newton's quotient in Maple, but what you do is you ask for the output as a plot, and you want to view it. This gives you your x range that you want to view. This is your y range. I could have gone from 0 to 1. Wouldn't have been any loss. As a matter of fact, let me change that because I can do that dynamically. And it will go ahead and recalculate for me. Because I'm never going into the negative quadrant, the fourth quadrant, I might as well, or the third quadrant for that matter, I might as well just plot this thing. Notice this is the point I want to evaluate at. This is the forward finding route. You can do the same thing backward finding. Doesn't matter which direction you go in. All right, notice that the answer for 1, as my computer jumps all over the place, I'm very sorry. I have to wait for it to recalculate everything. Notice that it's 0.5, right? So that's quite bad. And of course, I don't know why it didn't actually give me that graph. There we go. This is the point that I'm trying to evaluate, right? And that's my forward point. So it's taking the slope between those 2 points. And you can tell that there is a tremendous amount of deviation between those 2 points. If I come down and I cut that delta x, right, that h value in half to 0.5, I get closer to the actual value. It's 0.724. I'm still fairly far away from my 0.8775. If I plot that, you can still see that there's a fair bit of distance between those 2 points. And the actual curve and that secant, or the slope of that line. If I then cut that down from 0.5 to 0.1, I'm good to about 2 decimal place accuracy. I'm 0.85. Again, I was looking for the 0.8775. So really, I'm good to 1 decimal place accuracy. All right, with this forward-looking point. Way down here, I've got a lot of variation. To the left of the point, to the right of the point, I start to widen out. But between the 2 points, I'm getting closer. This is, in essence, doing exactly what you were doing in calculus class. You're taking a limit as this goes closer and closer to the actual point as h gets closer and closer to 0. If I cut h down to 0.05, I get 0.865. Again, I'm only good to 1 decimal place accuracy, even though my h has gone to 0.05. If I go to 0.001, I am now at 0.8773, and that gets me closer to my actual value, 0.8775. So I had to go out to 3 decimal place accuracy in h to get 3 decimal place accuracy in my slope value. That's not so good. I mean, that's fairly computationally heavy, and I would prefer not to do that if I didn't have to. So here, what we've got, if you remember, I said, it's very intensive, or it's very dependent upon the method used. What we're going to do is the center finding method. I'm going to take the value I want to have the slope at and take half of the h, go in front, half of the h, go behind the point, and then estimate the center point or the slope at that midpoint. To do that in Maple, what we do is we have to turn central on. So we just say central equals true, and now we'll use the center finding method. If I just go to my h equal to 1 again, now if I go back up to the top, my forward finding method for h equal to 1 was abysmal. Wasn't even close. If I come down here to my center finding method at h equal to 1, which should be abysmal, remember this h is going to take half of this. So it's actually going to take the midpoint, 0.05, go 0.05 in front, 0.05 behind, and it's going to find the slope between those 2 points for the center finding method. I'm already good to 1 decimal place accuracy. So if you have to do a numerical differentiation for some reason, you absolutely want to use the central finding method. The Taylor method that they outline in your readings is also very, very good. And the central finding method is actually a part of that. It can be derived from that, as the error of it can be derived from that. But if you're just looking for a quick and dirty method, absolutely go ahead and do this. Notice that I do the central finding method when I plot it. Right, that's the point, right, dead center that I want to evaluate this thing. It's at 0.5. I go negative 0.5. I go down to 0. Right? It tells me that's the one extrema. This is the other extrema at 1, where it is going to evaluate this thing. Right? So those are the 3 points that it's using to do this evaluation. Right? And it's exactly the same amount of time. It's exactly the same computational power. It's just that it's giving me a whole lot more accuracy, a whole lot faster. If I go to that h equal to 0.5, again, with the forward finding method, it was terrible. All right, I am getting much closer. If I round off to 2 decimal place accuracy, I get 0.87, right, because it's 0.868. All right, that's going to be, bang on for 2 decimal place accuracy if I round up. Again, because it's 0.05, I'm going 0.25 on either side. You can see how close this actually is. I now go to an h of 0.1. It's when I just barely started to get accuracy in the forward finding method. Notice I instantly get 3 decimal place accuracy here. It's 0.8772. Right? And, I changed the axis to go from 0 to 0.75 and from 0 to 1 just because otherwise you couldn't tell the difference in the 2 lines. They are that close together at this point. If I shrink it to 0.05, even by shrinking this to my x ranging from 0.45 to 0.59 and 0.4 to 0.55, you can't tell the difference in those 2 lines until you get way out here, which is well past the interval where I want to evaluate this thing. It's giving me great accuracy. If I truncate it at 4 decimal places, right, and round up, I get 0.8775. Right? I am bang on. Right? And if I go out to the 0.001, which I had before, I am good to 1, 2, 3, 4, 5, 6, 7 decimal place accuracy right off the bat. All right, so again, if you have a choice between using the forward finding method and the central method, you want to use the central method for this. This type of method is going to come back again. You will see this when we do first order differential equations. This will be akin to Euler's method and improved Euler's method when we do those. So you will see this again. Make certain that you understand this and how it's working because it's going to speak to your homework problems that you're going to have to do and some of the actual projects this time around. Because you are going to do problems for your projects. You're going to crank some problems for me to do integration and differentiation rather than just sit here and, answer multiple choice questions. So